All right, guys, this is the AI hitchhiker here. Voice a bit rusty, need some water. So today, this very early morning, and apologies, I need to speak a bit undertone because my family is sleeping, and I have decided not to sleep because I did my sleeping immediately after my 9 to 5 today. So, yep, I've got some time to work on my personal projects. And today I'm going to study from now to about 6 in the morning. I'm going to be studying AI engineering. And the book I'm going to be studying is one of the most recommended books in AI. I follow a lot of content creators in AI, and not just content creators, people who matter, whose opinion and voice matter when it comes to AI. And this is one of the books that most of them have recommended. And I've been looking forward to the opportunity to devour it because, you know, when it comes to AI and creating AI products and services, anybody can claim that it's easy to do, but I believe that to be able to do it well and to, deploy very robust AI products to the market, to people, then one really needs to learn it very well. So I'm a AI hitchhiker, meaning I'm no expert. I'm at the very beginning of my journey trying to be an expert in AI. So yeah, I want you to join me in my learning experience. And if you are watching this, the recording, I believe that most people will be sleeping, especially in my time zone, because it's 1:13 as I'm speaking now in the morning. So it will take a crazy person like me to be awake uh, studying AI engineering. But hey, if you watch the recording later, I hope you join me on this journey so that we study together. So having said that, I'm going to stop the long talk and start sharing my screen, and we'll start studying. Okay, so I'm just gonna make myself smaller. Okay, brilliant. So the book that I want us to study is AI engineering, publishers being O'Reilly. So AI engineering, building applications with foundation models. And this book was written by Chip Huyen. Chip Huyen, right? So, um, obviously, it's got copyright. Uh, And what does it say in terms of the copyright? O'Reilly books may be purchased for educational, business, or sales promotional use. Online editions are also available for most titles. More information, contact our corporate, blah, blah, blah. So, when it says business or sales promotional use, I'm assuming that I can share my screen with you guys whilst I read and study from this book. However, I'm not going to be sharing my screen throughout because I also want to share my um, notes that I am writing down. So I do my notes using a Notion, I'm going to show you guys the screen for my notes also. I've already prepared it. So this is my notes screen. I've already prepared it. So I've got my learning notes chapter by chapter. So when I start studying the chapters, I'll be putting my notes here. So I'll be switching between the screen for the book and the screen for my notes so that I wouldn't share everything in the book, because I'm not sure whether Chip is going to be happy that I'm sharing everything in the book. So I'll be switching between the screens. Right? Okay, brilliant. So let's go back to the book. All right, so here we go again. So, table of contents. So this book obviously has got 10 chapters, as you may have seen already. And I'm going to quickly mention the chapters. As you can see, chapter 1 is Introduction to Building AI Applications with Foundation Models. Then chapter 2 is Understanding Foundation Models. Chapter 3, Evaluation Methodology. Chapter 4, Evaluate AI Systems. Chapter 5, Prompt Engineering. Chapter 6, RAG and Agents. Chapter 7, Fine-Tuning. Chapter 8, Dataset Engineering. Chapter 9, Inference Optimization. And Chapter 10, AI Engineering Architecture and User Feedback. Now, if we break it chapter by chapter, then we've got the first chapter. The book talks about the rise of AI engineering. Then it moves to foundation model use cases. Then it comes to planning AI applications. Then the AI engineering stack. And there's a summary. Then chapter 2, that is understanding foundational models. The book talks about training data, modeling, post-training, sampling, then a summary. Then when it comes to chapter 3, the evaluation methodology, talks about challenges of evaluating foundation models, understanding language modeling metrics, then exact evaluation, AI as a judge, ranking models with comparative evaluation, then it's a summary. Then chapter 4, which is evaluate AI systems, you start with evaluation criteria, then we have model selection, then design your evaluation pipeline, then a summary. And 5, prompt engineering. We have intro to prompting, then prompt engineering best practices. Then we've got defensive prompt engineering and a summary. Chapter 6, there's the RAG and agents. We've got RAG. And that leads us to agents. And chapter 7, fine tuning. We've got fine tuning overview, memory bottlenecks, and fine tuning techniques. Chapter 8, which talks about a data set engineering. It's got data curation, then data augmentation and synthesis. We have data processing. Then chapter 9, inference optimization. It talks about understanding inference optimization, inference optimization. Why did I say inference? Inference. Okay. We have AI engineering architecture and user feedback, which is the last chapter. It talks about AI engineering architecture, then user feedback. So that's going to be the journey. So it's got about 492 pages in all. I mean, if obviously if you take away parts of the book which is not like the core book, and so if we see, Yeah, so if we start from here, yeah, so this is from page 1, chapter 1. Then if you come to chapter 10 and you go through everything and you say that you're done, then it means that we've got about how many pages to go? How many pages? How many pages? That gives us okay, still going. Okay, let me just hit epilogue and scroll up. No, I'm sure that will make me. Yes, the summary. So it's got 493. So let's say that it's got 500 pages. So if we want to do this in a matter of a week, then on average, because I don't want to have a lot of parts for this book, there are a lot of books that I need to consume as I build my career in AI engineering. So I want preferably to do one book per week. Okay. So this book will try and do 100 pages per part. But of course, if I'm tired and I need to go and sleep, I wouldn't force myself. So that is the plan. If I look at chapter 2, let me go to chapter 3 and scroll up. Yes, so if we can go through chapter 1 and chapter 2 today, that would be great because from chapter 1 to chapter 2 is like 112 pages. So let's see if that will be achievable. Okay, so yep, let's start with chapter 1, Introduction to Building AI Applications with Foundation Models. Okay, right. If I could use only one word to describe AI post 2020, it'd be scale. The AI models behind applications like ChatGPT, Google's Gemini, and Midjourney are at such a scale that they are consuming a non-trivial portion of the world's electricity, and we are at a risk of running out of publicly available internet data to train them. Okay, the scaling up of AI models has two major consequences. First, AI models are becoming more powerful and capable of more tasks, enabling more applications. More people and teams leverage AI to increase productivity, create economic value, and improve quality of life. Yeah, obviously, there's no doubt about it. I think AI models, the models that power ChatGPT, Cloud, um, not just the LLMs, but okay, I think at a point my internet went off. I'm using Vodafone, and Vodafone has experienced a serious outage since yesterday in the afternoon. For those of you in the UK who uses Vodafone, you know what I'm talking about. But thankfully, I've got another broadband I can switch to. So yeah, if you saw just a bit of outage on my part, it's because Vodafone has got issues. Anyway, let's go on. So yeah, indeed, it is true. Second, training large language models, LLMs, requires data. This has led to the emergence of model as a service. Models developed by these few organizations are made available for others to use as a service. Anyone who wishes to leverage AI to build applications can now use these models to do so without having to invest upfront in building a model. Okay, so let me know this now. Model as a service. So just gonna switch to my notes. So the book talks about model as a service. Model as a service. And model as a service so model as model as a service is when AI companies make foundational models available for businesses and organizations who do not have the resources to build models from scratch. Yeah, so if you've got the resources, I think models as a service, AI models as a service, is one of the very good business prospects for people who have got the resources. Building AI models from scratch and selling it to, offering it as a service to businesses and organizations. And I think it's quite a good business idea for people who have got the resources. And so, in terms of resources, uh, you need, as the book says, you need compute resources and specialized talent. So we do not have the resources, so obviously about compute resources and specialized talent. Build models from scratch. Okay, right. Okay, so anyone who wishes to leverage AI to build applications can now use the models to do so without having to invest upfront in building a model. Yes. All right. Let's go back. Share back the big screen. Okay, so let's go on. So in short, the demand for AI applications has increased while the barrier to entry for building AI applications has decreased. This has turned AI engineering, the process of building applications on top of readily available models into one of the fastest growing engineering disciplines. Yeah, so I think that is what I stated, that um, models as a service, or if you the notes that I wrote earlier, models as a service, one of the things that will make engineering very, very attractive, because companies that want to offer AI models as a service will need people who have got a specialized talent, specialized knowledge in building these models. So it's either you start an AI company building foundational models and offering it as a service, or you get so good at it and a company that's got the money and the compute resources will employ you, pay you very well, and you build these models for the company. So either way, you can be part of the winning team or the awesome world of AI modeling and stuff. Okay. Building applications on top of machine learning models isn't new. Long before LLMs became prominent, AI was already powering many applications, including product recommendations, fraud detection, and churn prediction. While many principles of productionizing productionizing AI applications remain the same. Okay, so while many principles of productionizing AI applications remain the same, the new generation of large-scale, readily available models brings about new possibilities and new challenges, which are the focus of this book. Okay, so this point is really, really important, because I feel like people talk about AI, and by the way, machine learning is one of the subfields of AI. Okay, because sometimes people think that they are two separate things. AI is the umbrella term, and machine learning is one of the subfields of AI. Okay, just as deep learning is one of the subfields of ML, machine learning. And this point here is critical because for most people, people talk about AI and make it look like it is something that just happened. Now, the part of large language models doing magic for us, like ChatGPT and all of that, is became popular because of OpenAI's invention, ChatGPT. But machine learning models have been in existence for a long time and doing product recommendations, fraud detection, churn prediction. Your YouTube channel, before ChatGPT became so big, your YouTube channel was doing video recommendations for you. And that is a machine learning that has been deployed into the app that is doing that. It was already doing that before ChatGPT became a thing. So it's a very important point here. And I agree with the author here. Okay, right. Let's move on. So this chapter begins with an overview of foundation models, the key catalyst behind the explosion of AI engineering. I will then discuss a range of successful AI use cases, each illustrating what AI is good and not yet good at. As AI's capabilities expand daily, predicting its future possibilities becomes increasingly challenging. However, existing application patterns can help uncover opportunities today and offer clues about how AI may continue to be used in the future. Okay, to close out the chapter, I will provide an overview of the new AI stack, including what has changed with foundation models, what remains the same, and how the role of an AI engineer today differs from that of a traditional ML engineer. Okay, that's it's brilliant. So we're going to be looking at overview of foundation models. Then we'll move to the key catalyst behind the explosion of AI engineering. I think it's been partly mentioned from the beginning. Most companies don't have the compute resources and the specialized talent to build foundation models from scratch. So big companies like the Google and the OpenAI and the Meta of the world, they have the, and of course X, they've got the specialized talent and the compute resources, and they are building foundational models. And they need AI engineers to do that. So obviously that is a key catalyst behind the explosion of AI engineering. Okay, so we're also going to discuss a range of successful AI use cases and illustrating what AI is good and not yet good at. Yeah, that is very important because some people have overhyped expectation about AI, thinking that it can do everything. Yeah. So yeah, let's go to the rise of AI engineering. Foundation models emerged from large language models, which in turn originated as just language models. While applications like ChatGPT and GitHub's Copilot may seem to have come out of nowhere, they are the culmination of decades of technology advancements, with the first language models emerging in the 1950s. This section traces the key breakthroughs that enabled the evolution from language models to AI engineering. Okay, brilliant. So, again, this chapter really, really shines a light on the fact that language models have been with us since the 1950s. However, ChatGPT, made it popular. Okay, but it's been with us. The universities and most scientists actually worked on these things, but I think that the idea of bringing it to market, the productionizing, the productionizing of these language models wasn't something that was probably part of the motivation of those who developed it since the 50s. But it's been with us for a very long time. So I'm just going to put that in my notes. So the first LLMs, the third LLMs emerge in the 1950s. Okay, so from language models to large language models. While language models have been around for a while, they've only been able to grow to the scale they are today with self-supervision. This section gives a quick overview of what language model and self-supervision mean. If you're already familiar with those, feel free to skip this session. Okay, so yes, language models have been around since, but they weren't self-supervised. They were not able to grow to the scale they are today with self-supervision. That's the difference. I think that's probably why it never was sent to market, or it wasn't production. There wasn't that productionizing of these language models. Okay, so let's keep on going and see what this self-supervision is all about. Language models. A language model encodes statistical information about one or more languages. Intuitively, this information tells us how likely a word is to appear in text. A language model that encodes English should predict blue more than car. So language models encode statistical information about one or more languages. I believe what this means is that the language model predicts the next word based on the probability or the possibility of the word belonging to that context. So, for example, my favorite color, there it's likely going to predict blue instead of car because this context talks about color. So, car is not color. So, blue is the appropriate. Okay, so I think it makes sense. Okay, so he made some notes here. In this book, I use traditional ML to refer to all ML before foundation models. Okay, right. Let's go on. The statistical nature of languages was discovered centuries ago. In the 1905 story, The Adventure of the Dancing Men. Oh, I love history. Sherlock Holmes leveraged simple statistical information of English to decode sequences of mysterious stick figures. Since the most common letter in English is E, Holmes deduced that the most common stick figure must stand for E. Okay, so we all probably have heard of Sherlock Holmes. In his story, The Adventure of the Dancing Man, he used simple statistical information of English to decode sequences of mysterious stick figures. Okay, what's the meaning of stick figures? Since the most common letter in English is E, Holmes deduced that the most common stick figure must stand for E. Right. So I just want to find out what a stick figure is all about. Well, so I'm just going to copy this and ask what it is. I'm just curious to know what the mysterious stick figures are. The Adventure of the Dancing Man. Sherlock Holmes leveraged statistical information. Okay, so what does it stand for? Okay, so it says the mysterious stick figures that Sherlock Holmes decoded using statistical analysis are the dancing men from the story. Adventure of the Dancing Men, a story written by Sir Arthur Conan Doyle, was published in 1903 as part of the Return of Sherlock Holmes. So here's a breakdown. The cipher, the Dancing Men were a code invented by an American gangster and used to send secret messages. Each take fake. The case, Mr. Hilton Cubitt hires Holmes after his American wife, Elsie, becomes terrified by the figures. Holmes' statistical method. Holmes uses frequency analysis to break the code. He knows that the most frequent dancing man symbol must correspond to E, the most common letter in the English language. By finding other common letters and using known words like LC, his client's wife, he systematically deduces the entire alphabet for the code. Okay. Okay. So mysterious stick figures. All right. Let's go. So later on, Claude Shannon used more sophisticated statistics to decipher enemies' messages during World War II. His work on how to model English was published in his 1951 landmark paper, Prediction and Entropy of Printed English. Many concepts introduced in this paper, including entropy, are still used for language modeling today. In the early days, a language model involved one language. However, today, a language model can involve multiple languages. Okay, so if it was English, it was just English. But today, I think, yeah, if you look at the model that powers ChatGPT, GPT-4, GPT-5, all of those models, yes, now it can understand other languages. If you give it, I remember I gave ChatGPT simplified Chinese, and it was able to explain to me in English what it is. Yeah, so it's true. The basic unit of a language model is token. Okay. So the basic unit, I'm gonna write this, which is token. Token can be a character, a word, a part of a word like TION, depending on the model. For example, GPT-4, a model behind ChatGPT, breaks the phrase, I can't wait to build AI applications into 9 tokens, as shown in figure 1. So I can't, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Note that in this example, the word can't is broken into 2 tokens. So we've got can and the apostrophe T. You can see how different OpenAI models tokenize text on the OpenAI website. Yeah, interesting. So let's put something down in the notes. Basic unit of a language model is token. So a token can be word, character, out of a word, etc. It's basically, so for example, open AI tokenize I can't wait to build awesome models. To build awesome AI applications. I can't wait to build awesome AI applications. So we've got, so let's say we've got I, then we have can, then we have wait, and we have to build awesome AI application. Yeah, so it's tokenized. So this one is by OpenAI GPT-4. OpenAI GPT-4 GPT model. That's how it tokenizes this sentence. Okay, brilliant. All right. Let's send it back to the book and continue. Okay, so the process of breaking the original text into tokens is called tokenization. For GPT-4, an average token three-quarters the length of a word. So 100 tokens are approximately 75 words. Okay. Let's think about this a bit. So an average token is approximately three-quarters the length of a word. So if you have 100 tokens, it will be approximately 75 words. So if you have a text, a word, it can be broken down into three parts of a four. So if you have 100 tokens, that will make up about 75 words. Okay. The set of all tokens a model can work with is the model's vocabulary. The set of all tokens a model can work with is a model's vocabulary. The set of tokens a model can work with is the model's vocabulary. Okay. You can use a small number of tokens to construct a large number of distinct words, similar to how you can use a few letters in the alphabet to construct many words. Okay, the Mistral 8x7b model has a vocabulary size of 32,000. GPT-4's vocabulary size is 1,256. The tokenization method and vocabulary size are decided by model developers. Right. That's interesting. Right, let's put some notes down. I'm going to share back my notes. Okay, so you're just learning now, but the amount or the set of all tokens a model can work with is its vocabulary. The set of all tokens a model can work with is the model's vocabulary. All right, so the model's vocabulary is a set of all the tokens a model can work with. And you, that is the developer, the model developer can use a small number of tokens to construct a large number of distinct words. And it's just similar to how you can use a few letters in the alphabet. So, for example, you can just use the 5 vowels in the alphabet plus some few consonants to construct a large number of distinct words. Especially if you're good. I think basically it's like you playing Scramble and you've got just some few letters available and you have to use that to construct a large number of distinct words. So it's the same thing. You can use a small number of tokens to construct a large number of distinct words. So the Mistral 8x7b model has a vocabulary size of 32,000. So we can put this as an example in my notes. So for example, Mistral 8. It is 7B vocabulary 2000 GPT was size is 0.56. The tokenization method and vocabulary size are decided by the developers. Okay. All right. Okay, let's go on. Okay, so why do language models use, let me change back to the book. Sorry. I have to find a smarter way of doing this instead of the switching back and forth. All right, so why do language models use token as their unit instead of word or character? There are three main reasons. Number one, compared to characters, tokens allow the model to break words into meaningful components. For example, cooking can be broken into cook and ing, with both components carrying some meaning of the original word. Okay. Two, because there are fewer unique tokens than unique words. This reduces the model's vocabulary size, making the model more efficient. As to three, to also help the model process unknown words. For instance, a made-up word like church heating could be split into chat GPT and ing. Chat GPT, okay, could be split into chat GPT and ing, helping the model understand its structure. Tokens balance having fewer units than words while retaining more meaning than individual characters. Okay, right. So let's make sense of these three reasons. So the first one, again, compared to characters, tokens allow the model to break words into meaningful components. So for example, cooking can be broken down into cook and ing, with both components carrying some meaning. So the first reason is that tokenization, instead of just using as a unit, instead of using a word or character as a unit, helps break the word into meaningful components. So dancing or cooking, as they use an example there, cook and ing, it helps you to know that cook, which is meaningful, ing, meaningful. Ing was added to the cook because it's a continuous tense. Yeah, so helping you to break a word or the character into meaningful components. That is why tokenization is used. Makes sense? The second one, because there are fewer unique tokens than unique words. This reduces the model's vocabulary size, making the model more efficient. Okay, let's make sense of this. Fewer unique tokens than unique words. Yes. Okay, so how are tokens unique compared to words? If you look at the example that we did on I can't wait to build awesome AI applications, you can see that through tokenization, you can uniquely break this sentence into units, and it makes each token unique. But if you do it based on words, then if two words which are the same appear in a sentence or in a paragraph, then it won't have unique, they won't be unique. Can let you have unique words, unique units, if you like. Yeah. There are fewer unique tokens. Fewer unique tokens than unique words. This reduces the model vocabulary. Okay. It's rather the opposite. The tokens, there are fewer unique tokens than unique words. Okay. It reduces the model vocabulary size, making the model more efficient. So are we saying here that the fact that tokens are not too unique, we don't have a lot of unique tokens, helps? I thought it would rather be the opposite, where having more tokens making the breaking of the words into their component parts more unique is an advantage, but rather is an advantage because there are fewer unique tokens compared to unique words. Okay. Right. So number three, tokens also help the model process unknown words. For instance, a made-up word like chat GPT could be split into chat GPT and ink, helping the model understand its structure. Okay, tokens balance having fewer units than words. While retaining more meaning than individual characters. Okay, so the processing of unknown words helps with tokens because, for example, like you said, let's say Googling, okay, the token is able to break it to Google and ing or Google without the E and ing. So maybe Googling is not a known word, but a very relatively new unknown word. The token is able to handle it and process it. And that is why models use token as their unit instead of word or character. Okay, right. Let's note this down. I'm going to share my notes. Okay, so we have just learned two reasons why large language models use tokens instead of word or character. Not two, three reasons. So let's put it down in the note section. So three reasons, three main reasons, three main reasons why language models use tokens as their unit instead of word or Number one is because tokens help characters or words to be broken down into meaningful components. It allows the model. Tokens allow the model to break words down into meaningful components. Meaningful components. So an example is, oh, I don't want to use example in the book. An example is um, um, eaten. Okay. Can be tokenized into, so we can have, can be tokenized into eat ink. Yeah. So both tokens carry some meaning of the word. Both tokens carry meaning of the original. Okay, the next reason is the fact that tokens are less unique. There are fewer unique tokens than unique words. And the reason why this is good is that it reduces the model's vocabulary. The model's vocabulary, like I learned earlier on, is the set of all tokens that a model can work with. So if we have less unique tokens, it reduces the model vocabulary. So there are fewer unique tokens. There are fewer unique tokens compared to unique words. Thus, reducing the model's vocabulary, which is good because that will mean less compute resources used, I believe. And that is why tokens are good. Then tokens help process the models. It helps the model to process unknown words. Tokens help the model to process unknown words. Tokens help the model to process unknown words. So the example that they gave in the book is chat GPT. For example, chat GPT, which will be tokenized, as Chat GPT and INJ. Yeah, so um, this is good, and that is why tokens are perfect. Right, so let's go to back to the book. All right, let's go back to the book. Okay, so there are two main types of language models: masked language models and auto regressive language models. They differ based on what information they can use to predict a token. Hmm. So their differences is based on what information they can use to predict a token. Masked language model and auto-regressive language models. Okay, so masked language model. The masked language model is trained to predict missing tokens anywhere in a sequence. They are trained to predict missing tokens anywhere in a sequence using the context from both before and after the missing tokens. In essence, a masked language model is trained to be able to fill in the blank. For example, given the context, my favorite dash is blue. A masked language model should predict that the blank is likely color. A well-known example of a masked language model is bidirectional encoder representations from transformers or BERT. Okay. As of writing, masked language models are commonly used for non-generative tasks such as sentiment analysis and text classification. They are also useful for tasks requiring an understanding of the overall context, such as code debugging, where a model needs to understand both the preceding and following code to identify errors. Let's pause a bit. Masked language models are commonly used for non-generative tasks. What does it mean by non-generative tasks? Okay, he gave an examples such as sentiment analysis and text classification. Okay, so it's not, those are not meant to generate tests, but rather sentiment analysis is like trying to analyze the sentiment that is being portrayed in a text. So, for example, social media text. So, the job of the model is not to generate text, but doing some analysis of the already existing text. Text classification is also a good example because you are not generating text, you are classifying the existing text. So, this masked language model, they are used for this kind of non-generative tasks. Okay, sentiment analysis, text classification. They are also useful for tasks requiring an understanding of the overall context. Okay, an understanding of the overall context, such as code debugging, where a model needs to understand both the preceding and following code to identify errors. It makes sense. because for them, for the model to be able to predict accurately, it should understand the context. The context here meaning the preceding and following code. The preceding, the test that the context, the test that comes before and after. That is context. Okay, so that is mixed language model. Right. Let's look at auto-regressive language model. Auto-regressive language model. An auto-regressive language model is trained to predict the next token in a sequence using only the preceding tokens. Trained to predict the next token in a sequence. Okay. They are trained to predict the next token in a sequence using only the preceding tokens. All right. So unlike the masked language model that uses the preceding, the before and the after, auto-regressive language models only uses the before. It predicts what comes next. In my favorite color is an auto-regressive model can continually generate one token after another. Today, auto-regressive language models are the models of choice for text generation. And for this reason, they are much more popular than mixed language models. Okay, so we've got this figure 1, 2 shows these two types of language models. You've got auto-regressive model, why does the chicken cross the then the context previous tokens only, this one. So it predicts why does the chicken cross there, then it's going to predict the next one based on the previous token. So it's going to look at the previous tokens and predict the next. That is auto-regressive language model. The mixed language model. So why does then the prediction will be, it will consider the preceding tokens and the token that comes after. Makes sense. Okay. Right. Okay, so in this book, unless explicitly stated, large language model will refer to an auto-regressive model. All right, cool. So let us put down some notes because we've just unpacked very two important concepts for large language models. So I'll go to my notes and put this down. Okay, so we are talking about two types of language. Two main types of language models. Two main types of LLM. It's not big, it's just language models. So we've got the mixed language model and auto-regressive. Okay, so the mixed language model predicts missing tokens in a sequence using the context from both before and after the missing tokens. Okay. So this one predicts missing tokens in a sequence using the context that before and after missing. Then the auto-regressive one, it predicts the next token in a sequence. It's the next token in a sequence using only the preceding tokens. Okay, so that is fast and auto-regressive. Okay, so a bit more about the mixed language model. It talked about let's give an example. An example could be my favorite is rice pudding. Yeah, so it will predict the missing token based on the before and after context. Okay, so well-known example of language model is is birational. Birational encoder. Birational, and encoder representations. Transform. I've got the big bird. Okay. So maxed language is mainly used for non-generative tasks such as sentiment analysis, and test classification. And the autoregressive, like we said, it predicts the next token in a sequence using only the preceding tokens. Okay, so for the autoregressive language models, it is mainly used for the generative tasks. Autoregressive language models. Are mainly used for generative tasks. And it is the most popular. So it's popular compared to the maxed language model. Alright, so maybe I could take a screenshot from the book and put it there. I'm just gonna take a screenshot from this book, put it here. All right. Okay, so as a screenshot from the book. Yep. Okay. So that is it. Okay. Brilliant. So let's go back to the book. All right, so in this book, unless explicitly stated, large language model will refer to an autoregressive model. Right. The outputs of language models are open-ended. A language model can use its fixed finite vocabulary to construct infinite possible outputs. A model that can generate open-ended outputs is called generative, hence the term generative AI. Mm, okay, let's read that paragraph again. The outputs of language models are open-ended. Okay, so we don't, it's not closed-ended. Closed-ended is like specific words, but this is open-ended. A language model can use its fixed finite vocabulary to construct infinite possible outputs. So, like we've already stated, by nature, the tokenization models process the tokens using very finite vocabulary. And that is one of the reasons why the tokenization is good. But then this finite vocabulary can be used to construct infinite possible outputs. So a model that can generate open-ended outputs is called generative, hence the term generative AI. You can think of a language model as a completion machine. Given a test prompt, it tries to complete that test. Here's an example. Prompt from user: to be or not to be. Completion from language model. That is the question. It's important to know that completions are predictions based on probabilities and not guaranteed to be correct. This probabilistic nature of language models makes them both so exciting and frustrating to use. Okay, we'll explore this further in chapter 2. So I remember when ChatGPT came, people were like, it's good, but it can be very bad. And what people did they understand that large language model, the generative AI, the large language model is probabilistic. It's not deterministic. It's probabilistic. So if you're being now it's been good. For example, GPT-5 from OpenAI is quite good, but when they started, when the model that was powering ChatGPT, I think model 3 or so, it was very, 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 very probabilistic. It was predicting a lot, and because of that, it wasn't giving deterministic answers. Okay, but if you use it for something that is creative, where it has to use its creative power, you could see how it did a very good job. So, for example, you ask it to create an ode, a poem, and it's able to do it because that is the true nature of this generative AI, is to creatively come with a text, creatively complete the assignment that you have given them instead of being very specific and deterministic in their response. Now, it can give very good deterministic answers. With, let's say, if you take the models that power cloud and ChatGPT and any large language model or any generative AI service or product that you use now, it can gives very good, correct, deterministic answers. But like you've just read from here, its job is really to be predictive and as a result of that, be more creative rather than being deterministic in their answer. Okay, so that is the large language model for you. Okay, let's move on to the next page. Hmm. As simple as it sounds, completion is incredibly powerful. Many tasks, including translation, summarization, coding, and solving math problems, can be framed as completion tasks. For example, given the prompt, "How are you" in French, is a language model. Sorry. For example, given the prompt, oh, sorry. For example, given the prompt, "How are you" in French is a large language model might be able to complete it with comma server effectively, translating from one language to another. As another example, given the prompt question, "Is this email likely spam?" Here is the email. Answer. A large language model might be able to complete it with likely spam, which turns this large language model into a spam classifier. While completion is powerful, completion isn't the same as engaging in a conversation. For example, if you ask a completion machine a question, it can complete what you said by adding another question instead of answering the question. That is post training on page 70 and discusses how to make a model respond appropriately to a user's request. Okay. Yeah, makes sense. Self supervision. Language modeling is just one of many ML algorithms. There are also models for object detection, topic modeling, recommender systems, weather forecasting, stock price prediction, etc. What's special about language models that made them the center of the scaling approach that caused the ChatGPT moment? What what's special about language models that made them the center of the scaling approach that caused the ChatGPT moment? The answer is that language models can be trained using self supervision, while many other models require supervision. Supervision refers to the process of training ML algorithms using labeled data, which can be expensive and slow to obtain. Self supervision helps overcome this data labeling bottleneck to create larger data sets for models to learn from, effectively allowing models to scale up. Here is how. With supervision, you label examples to show the behaviors you want the model to learn, and then train the model on these examples. Once trained, the model can be applied to new data. For example, to train a fraud detection model, you use examples of transactions, each labeled with fraud or not fraud. Once the model learned from these examples, you can use this model to predict whether a transaction is fraudulent. The success of AI models in the 2010s lay in supervision. the model that started the deep learning revolution. AlexNet, Krzyzewski et al. 2012 was supervised. It was trained to learn how to classify over 1 million images in the dataset ImageNet. It classified each image into one of 1,000 categories, such as car, balloon, or monkey. A drawback of supervision is that data labeling is expensive and time consuming. If it costs 5 cents for one person to label one image, it costs 50,000 USD to label a million images for ImageNet. If you want two different people to label each image so that you could cross-check label quality, it costs twice as much. Because the world contains vastly more than 1,000 objects, to expand models' capabilities to work with more objects, you will need to add labels of more categories. To scale up to 1 million categories, the labeling cost alone would increase to 50 million USD. Wow. That is quite an eye opener there. So supervision, training models through supervision, quite expensive here. Labeling everyday objects is something that most people can do without prior training. Hence, it can be done relatively cheaply. However, not all labeling tasks are that simple. Generating Latin translations for an English to Latin model is more expensive. Labeling whether a CT scan shows signs of cancer would be astronomical. Self-supervision helps overcome the data labeling bottleneck. In self-supervision, instead of requiring explicit labels, the model can infer labels from the input data. Okay, so I think self-supervision here will be what we call unsupervised learning. Okay, so the model infer labels from the input data. Language modeling is self-supervised because each input sequence provides both the labels, tokens to be predicted, and the context the model can use to predict these labels. For example, the sentence, "I love street food," gives 6 training samples, as shown in table 1.1. Okay, so let's look at table 1.1. Training sample from the sentence, "I love street food," for language modeling. So the input context and the output, let's take an I. Okay, love, street, food. All right. In table 1.1, BOS and EOS mark the beginning and end of a sequence. These markers are necessary for a language model to work with multiple sequences. Each marker is typically treated as one special token by the model. The end of sequence mark is especially important as it helps language models know when to end their responses. Okay, so this is similar to how it's important for humans to know when to stop talking. Okay, so this is how it's trained. All right. Self-supervision differs from unsupervision. Okay, so I thought self-supervision is unsupervised learning, but it says it differs from it. Okay, let's hear it. In self-supervised learning, labels are inferred from the input data. Okay, labels are inferred, so it's still labels, but they are inferred from the input data. In unsupervised learning, you don't need labels at all. So, supervised learning and self supervised learning, labels are needed. For supervised learning, you, the one training the model, needs to provide the labels to the model. But in self supervised learning, the labels are inferred from the input data. The model infer the labels from the input data. And that's what normally happens for LLMs, especially for the autoregressive large language model. I think the must language model also does that. Yeah, but I think autoregressive language model will probably be the best example here. Okay, so self-supervised learning means that language models can learn from test sequences without requiring any labeling. Because test sequences are everywhere in books, blog posts, articles, and Reddit comments, it's possible to construct a massive amount of training data, allowing language models to scale up to become LLMs. LLM, however, is hardly a scientific term. How large does a language model have to be considered large? What is large today might be considered tiny tomorrow. A model size is typically measured by its number of parameters. A parameter is a variable within an ML model that is updated through the training process. In general, though, this is not always true. The more parameters a model has, the greater its capacity to learn desired behaviors. Okay, that's quite interesting. When OpenAI's first generative pre-trained transformer GPT model came out in June 2018, it had 117 million parameters, and that was considered large. In February 2019, when OpenAI introduced GPT-2 with 1.5 billion parameters, 117 million was downgraded to be considered small. As of the writing of this book, a model with 100 billion parameters is considered large. Perhaps one day this size will be considered small. Okay, I understand the point. So, what is considered large today can be considered large, can be considered small tomorrow. So, large language model, the word large is not scientific because GPT model that powered ChatGPT when it was released in June 2018 was considered large. But just after a year, it was considered small. And currently, what is considered large is a model with 100 billion parameters. That is crazy. I'm sure that whilst the world is talking about artificial general intelligence, I'm sure a model that powers an artificial general intelligence would be in quadrillions. And that will make the 100 billion parameter model small in comparison. Right. Before we move on to the next section, I want to touch on a question that is usually taken for granted. Why do larger models need more data? Larger models have more capacity to learn and therefore would need more training data to maximize their performance. You can train a large model on a small data set too, You can train a large model on a small data set too, but it will be a waste of compute. You could have achieved similar or better results on this data set with smaller models. Makes sense. Okay. Right. Do I need to put something down? I think. Yeah, so I just want to let me go to my notes and put something down. Okay, I'm just gonna go to my notes. All right, let's put something in the learning notes. So we have learned yeah, let me just rearrange this quickly. So I think this should have just have to make sure that we have got um, it in the right place. I'm just gonna cut this, bring it here. Yep, and just take this part, put it here. This one should actually be that. All of these were about tokens. Yes, the two main types of language models. I'm gonna cut this and I'll put here and I will cut this whole talk about tokens. Put it here. Oops. Um set of tokens that a model can work with is the model's vocabulary. The three main reasons why language models use languages to capture units instead of word or character. So this would be a child that This is going to be a child of that. Two main types of language models. Two main types. That and I'll also this. Yep, and I will bring this one and make it a child of the one on top. This is also going to be a child of, sorry, going to be a child of this one. This will be a child of the one. This will cut and cut here. And we will yeah, brilliant. So now let's put in our thoughts. So there are three concepts that we've mentioned here. We've talked about um, self supervised versus supervised. We read from places that language models are trained through self supervision, which is different from unsupervised. Unsupervised learning. Self-supervision. The self-supervision learning uses labels from the input data to train the model. Whereas whilst unsupervised learning does not use labels at all. Now I have to state why large language models or language models uses self-supervised learning. Self-supervised learning is cheap. Self-supervised learning is cheaper compared to supervised learning when it comes to training language models. Models for completion tasks. It is cheaper because this can come as a sub point. So why is it cheaper? It is cheaper because the model developer it's cheaper because the language model learns the labels in input data, and as a result, the model developer does not have to spend resources providing labels. Alright. In the case of supervised. Okay, brilliant. Okay, all right. So, point made. Let's move on, and I will share back my screen to the book. So it says here the actual data labeling cost varies depending on several factors, including the task complexity. The scale, larger data sets typically result in lower sample costs in the labeling service provider. For example, as of September 2024, Amazon SageMaker Ground Truth charges 8 cents per image for labeling fewer than 50,000 images, 42 cents per image for labeling more than 1 million images. Okay. But it's still expensive. But if you are being charged 2 cents per image for labeling more than 1 million images, that is how much? 2 cents is like, let's say 0.02. I'm assuming it's 0. Maybe 0.02. Yeah. Times 1 million. 6 zeros. That is about 20,000 USD training 1 million images. Where 8 cents per image was charged. That is quite a lot. Yeah. I think it's one of the reasons why language models are popular. Because it doesn't involve too much when it comes to training the model. Because of the self-supervised nature. Okay. Right, from large language models to foundation models. While language models are capable of incredible tasks, they are limited to tests. As humans, we perceive the world not just via language, but also through vision, hearing, touch, and more. Being able to process data beyond text is essential for AI to operate in the real world. Okay. For this reason, language models are being extended to incorporate more data modalities. GPT 4V and Cloud 3 can understand images and text. Some models even understand videos, 3D assets, protein structures, and so on. Incorporating more data modalities into language models makes them even more powerful. OpenAI noted in their GPT-4V system card in 2023 that incorporating additional modalities such as image inputs into LLMs is viewed by some as a key frontier in AI research and development. While many people still call Gemini and GPT-4V LLMs, they are better characterized as foundation models. The World Foundation signifies both the importance of these models in AI applications and the fact that they can be built upon for different needs. Foundation models mark a breakthrough from the traditional structure of AI research. For a long time, AI research was divided by data modalities. Natural language processing (NLP) deals only with text. Computer vision deals only with vision. Text-only models can be used for tasks such as translation and spam detection. Image-only models can be used for object detection and image classification. Audio-only models can handle speech recognition, speech-to-text, or STT, and speech synthesis, text-to-speech, or TTS. A model that can work with more than one data modality is also called a multimodal model. I love it. A generative multimodal model is also called a large multimodal model, LMM. So LMM is better than LLM. If a language model generates the next token conditioned on text only tokens, if a language model generates the next token conditioned on text only tokens, a multimodal model generates the next token conditioned on both text and image model and tokens, or whichever modalities that the model supports, as shown in figure 1.3. So we've got text tokens, visual tokens, multimodal model. So I think if you look at GPT, it's a multimodal model now. It generates images. The only thing it can generate now are videos. And I think it's because they've got a separate video model that is Sora. They've come with Sora 2 now. Yeah, but I love LMMs, large multi-model models, like large multimodal model, large multimodal model. I think people talk about LLMs, but the models that power ChatGPT, that power Claude, all of that, they are no LLMs. They are not just text models. They are also image models. They are audio models. They've got a lot of modalities, and that is great. Just like language models, multimodal models need data to scale up. Self-supervision works for multimodal models too. For example, OpenAI used a variant of self-supervision called natural language supervision to train their language image model Clip. OpenAI 2021. Instead of manually generating the labels for each image, they found image test pairs that co-occurred on the internet. They were able to generate a data set of 400 million image test pairs, which was 400 times larger than ImageNet without manual labeling costs. This dataset enabled Clip to become the first model that could generalize to multiple image classification tags without requiring additional training. Okay, so this book uses the term foundation models to refer to both large language models and large multimodal models. Okay, so before I go on, it is important I make note of large language models and large multimodal models. So I will go to my notes section and let's do some notes here. Okay, so I'm gonna put down some notes. So we just studied or talked about what is known as large language models, LLMs, which is what everybody knows, versus large multimodal models, LMs. So LLMs are test models. So LLMs are models trained on test only. LLMs are models trained on test only. However, only then LMMs are models trained on several modalities. Is that a word? Yeah. Trained on several modalities, such as text, image, audio, etc. Most models, both LLMs, both LLMs so let me give an example. So for example, Gemini and GPT. Gemini and GPT models are not LLMs as most people think, but they are LMS because they don't only produce text, they produce images. So they are large language models. The correct hand encapsulate L L. Okay, so the umbrella term is foundational models. Which is better? So if it's a foundational model, it encapsulates everything. Okay, so right. Right, let's go back to okay. So let's go on. Know that Clip isn't a generative model. It wasn't trained to generate open-ended outputs. Clip is an embedding model trained to produce joint embeddings of both text and images. Introduction to embedding on page 134 discusses embeddings in detail. For now, you can think of embeddings as vectors that aim to capture the meanings of the original data. Okay. You have generative models, the models that produce open-ended response, and we have the embedded models, for example, Clip. And we can think of embedded models as the vectors that aim to capture the meanings of the original data. Vectors that aim to capture the meanings of the original data. The multimodal embedding models like Clip are the backbones of generative multimodal models, such as Flamingo, Lava, and Gemini, previously barred. Foundation models also mark the transition from task-specific models to general-purpose models. Yeah, previously, models were often developed for specific tasks such as sentiment analysis or translation. A model trained for sentiment analysis wouldn't be able to do translation and vice versa. Foundation models, thanks to their scale and the way they are trained, are capable of a wide range of tasks. And I think that is what people don't like. People would be, especially those who advocate for AI safety, they will be happy with models trained for a specific task. But when a model is trained and it can do almost everything, it becomes too powerful. And that is why ChatGPT is becoming now the model that powers ChatGPT. The current model being GPT-5. they is it can do almost anything you think of. It can, yeah, it's becoming very powerful, and I think that is what a lot of people are worried about when they think about AI safety. If ChatGPT became just a large language model so that it was only for test completion, then maybe people wouldn't be so worried about it. But yes, case that the founders of ChatGPT, if you listen to some Altman's interview, he's quite excited about uh, general artificial intelligence, even though he expressed some anxiety about it. It doesn't mean that if they have to release the model that will send us into general artificial intelligence, they won't do it. He will do it, you know. Yeah. So foundation models is what is in vogue now, but that is what is creating all of the anxieties around AI. Out of the box general purpose models can work relatively well for many tasks. An LLM can do both sentiment analysis and translation. However, you can often tweak a general purpose model to maximize its performance on a specific task. Figure 1 to 4 shows the tasks used by the supernatural instructions benchmark to evaluate foundation models. 1 et al. 2022, providing an idea of the types of tasks a foundation model can perform. Imagine you are working with a retailer to build an application to generate product descriptions for their website. An out of the box model might be able to generate accurate descriptions, but might fail to capture the brand's voice or highlight the brand's messaging. The generated descriptions might even be full of marketing speech and cliches. Yes. The range of tasks in the supernatural instructions benchmark. Okay. All right. Oh, okay. That's quite a lot. Translation causing. Okay. Wow. All right. There are multiple techniques you can use to get a model to generate what you want. For example, you can craft detailed instructions with examples of the desirable product descriptions. This approach is prompt engineering. You can connect the model to a database of customer reviews that the model can leverage to generate better descriptions. Using a database to supplement the instructions is called retrieval augmented generation, RAG. Retrieval augmented generation. It's powerful. Connecting the model to a database. You can also fine tune, further train the model on a data set of high quality product descriptions. Prompt engineering, RAG, and fine tuning are three very common AI engineering techniques that you can use to adapt a model to your needs. The rest of the book will discuss all of them in detail. Okay. Hmm. Adapting an existing powerful model to your task is generally a lot easier than building a model for your task from scratch. For example, 10 examples, 10 examples in 1 weekend versus 1 million examples in 6 months. Foundation models make it cheaper to develop AI applications and reduce time to market. Exactly how much data is needed to adapt a model depends on what technique you use. This book will also touch on this question when discussing each technique. However, there are still many benefits to task specific models. For example, they might be a lot smaller, making them faster and cheaper to use. Whether to build your own model or leverage an existing one is a classic buy or build question that teams will have to answer for themselves. Discussions throughout the book can help with that decision. Okay. So, for example, I think I was having this discussion in my company. Okay, not really discussing with anyone, but I was thinking of it. Since my company is really concerned about data protection, we could build a foundational model specifically for my company. I'm talking about credit bureau agencies, or or they could we could use an existing foundational model, for example, Copilot, Microsoft Copilot, the model that powers Microsoft Copilot, and use prompt engineering to try to get response from the model, or rack, connect the model to our database of information, rack, the augmented um, thing that we talked about, retrieval augmented. What's the full name of rack? Apologies. Retrieval augmented generation. Or we can do fine tuning. Because it is every company that wants to embrace AI should decide either you're going to build a foundational model from scratch or you pick an existing foundational model, for example, GPT-5. Then you connect your database to the model. That will be RAG, retrieval augmented generation, or you don't connect your database to RAG, but you um, just use prompting to try to get responses from the model, or you do fine tuning of the model in order to get it to do what you want it to do. Yeah. So AI engineering, I believe, is what is basically these things. Yeah, and if somebody calls himself an AI engineer, he should be able to do these three things: being able to build foundational models from scratch, or taking an existing foundational model and making it do a specific task through prompt engineering or fine tuning the model, or RAG, retrieval augmented generation. Okay, brilliant. Um, I really need to pause here. It looks like, unfortunately, there is no pause for my life, but we'll do a part two, maybe when I come back, because I'm not going to sleep yet, but I need to take a break. So, for those of you who are watching me, I've seen two people who joined me from YouTube. I'm really grateful for spending time with me. Please leave a comment or a feedback for me. Yeah. And if you've got any thoughts that you want to share, you can share with me. I will be back with more learning. But for now, I'm going to take a break. And yeah, thank you for joining. And as we all keep learning, um, we'll get better at this thing. And hopefully, by the end of going through the book, those of you who are watching and learning with me, all of us will be able to get the skills to build AI models, foundational models from scratch, or better still have the skills to be able to um, prompt a model very well to be able to do specific tasks, or fine tune the model, or what most companies are doing now, build a RAG, a retrieval augmented generation pipeline or architecture, uh, connecting it to a particular model like GPT models. So thank you for joining. We'll definitely do a part two, maybe in some few minutes or in some few hours time to come. But we need to take a break because sitting too much is not good. Right? We will speak later. Bye for now.